take. So let me spend some time on the homework. I guess some of you guys are interested.
Yeah.
So for the homework, so for the first question, basically it's saying, okay, I guess some of you guys misunderstood the question. Like X is, we're saying that we have a kind of tournament or something like two teams, right? We have A and B, and then the first team that's win for 3 games, then it will win the tournament. So therefore, the outcome can be either A, that team A continue to win, or you can have B, A, something or you can have B, A, stuff like that. Right? These are the outcomes, what I'm saying. So therefore, some of you think the outcome is just A win or B win. No. We call the random variable that the outcome of this whatever tournament is X, but this outcome is not just A win or B win. It's whether it's A, B, B, and so on, and so forth. And then we define Y, so it's clear how and then we define Y as the random variable that is the number of games that actually plays. So therefore, this basically, this is Y is equal to 3, Y is equal to 4, and this is Y equal to 5, right?
That's right.
And so if I want to okay, the first question asks you what is hx? So it's a simple counting kind of compilatory that kind of problem. So basically, how many different games outcome to have Y, length of the will be just A and B, right? And for this one, there will be kind of I think there will be 6 of them. For this one, basically you can have B, A, B, A, and then so on. Then you have B, A, B, 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 and B, so on. Then you have 6 of them.
Sir, A, B is we cannot count that. A, B.
No, it's not A, B. It's A, B.
But A, B, there is no A, B.
That's not A, B. I didn't write A, B here.
Can we put A, B on there?
No, we cannot have A, B, right?
Oh, okay.
Yeah. So, and then for 5, Y equal to 5, we can have this one, and then basically the combination will be something okay, assuming A win, then you have the last one will be A, right? And then basically either and then for the rest of the 4 games will be A will win 2 of them, and B wins 2 of them. So therefore will be just 4C2 for A winning that. So that would be so 6 of them for A wins and 6 of them for B wins. So that should be 12 of them basically, right? So that would be all the counting. So then I guess some of you make the mistake here is be very careful, not each of these combination has the same probability, right? Actually, in the homework problem, I forgot to give enough information, but all of you guys are smart enough just make the assumption. Basically, I'm saying I didn't mention that. Okay, I assume both A and B have equal kind of probability of winning each game. So then, but then in that case, assume probability of A winning is 0.5, on probability B winning is 0.5 for each of the game, and then for probability of each of these combination will be 1/2 to the cube, right? yeah, A win, like probability A win in the first game is 1/2, probability A win in the second game is 1/2, probability A win in the third game is 1/2, right? So it's 1/2 to the third. But for this guy, like if the game, that whole tournament, like consists of 4 games, then probability will be 1/2 to the fourth, right? And then like for this one, it's actually 1/2 to the fifth. And if you do the counting, so how many of these will be like each of these I have two of them, right? So I have like 2 1/2 to the third, and then I have like 6 of them, like 1/2 to the fourth. I won't write 6 of them, there will be 6 of them. And then I have like 12 of them is 1/2 to the fifth, right? I'm not sure you can verify that because like these are probability, right? If you sum up all this, should get you 1. This is the probability of like each of the possible outcome, right? The outcome that this is the outcome for AAA, let's say. This is the outcome for BBB. And this is like BAAA, ABA, so on and so forth.
Why 1/2, 1 or 2? Why?
Here, oh, okay. As I said, like we assuming that like probability A win a game is equal to probability B wins a game here.
So 50-50.
50-50, yeah, 50-50. So then, for example, like AAA will be like A first win in the first game will be 0.5 by probability, and then again the second game will be 0.5, and the third game is again 0.5, so it will be 0.5 to the cube, right?
I think we don't have that information.
Oh yeah, that's I forgot to. But the most important, you can put PQ here, right? You can put like probability A win is P, probability B win is 1 minus P, and so on, right? If we make stuff more complicated, basically this will be P cube. For example, this is a 1/1 minus P, let's say, call it Q. This will be Q cube, let's say. And then this will be like P or whatever. If you do it this way, like I will count you as correct as well. But you cannot just assume these will be equal. There's no way like the probability of AAA will be equal to like probability of BAAA. Yeah. So but let's assume this simple case, like they are equally likely to win, then like this will be all the probability, right? Then you can compute the entropy will be just like 1/2 third log 1/2 third plus blah blah blah, like a long list of them. And then if you compute that, this will be like 4.125, something like this. This is HX. And then HY if like you do this counting correctly, your HY will be correct as well. So then like the probability y equal to 3 will be basically sum of these two, right? So therefore it's equal to okay, y equal to 3 is 1/2 times 2, right? And then probability y equal to 6 is 1/2 to the 4th times 6. Oh, sorry, not 6, I'm sorry. Y equal to 4.
10 4.
Yeah, y equal to 4. Like I mean, like, and then y equal to 5. We have probability 1/2 to the 5th times 12. Yeah, so therefore like HY would be like something like 2 1/2 third log 2 1/2 third plus 1/2 log this is not. Oh, yeah. I got confused myself. Anyway, let's say 1/2 5th and 12 log. Something like that, right? Have a minus sign, yeah, just that. So, and if you put into the calculator or computer, you will get like 1.56 bits. And then you have C part, D part, and E part. Like I just like go through the order. I randomly ask the joint entropy and conditional entropy. I didn't think of like which order is easy to compute. So so let me compute D first because that order is easy actually. So hy equal given x. What is hy given x?
Sorry?
What was hy given x?
Oh, xy minus x, hx.
Yes, but in this case, what's hy given x?
Yeah.
Just for this problem, like what is hy given x?
We don't have xyx in there. We don't have that. Yeah.
No, just think of like what is hy given x like for this particular problem here.
Oh, that should be summation.
No, actually, you don't even need to get into the equation, right? Because think of what is x and what is y here, right? X is like this kind of outcome, whether it's like by the end of the tournament, whether you have AAAA, BBBB, or BAAA, and so on and so forth, right? And y is basically the length of that tournament, right? Number of games, right? So knowing x, of course, you will know y, right? I mean, given x, y is deterministic, right? So therefore, like hy given x is simply equal to 0, right? This is just equal to 0. Yeah. Right? I mean, like, let's say, what's x again? X is the outcome, whether it's the outcome means that like over the entire tournaments, which team win what game, right? So the outcome can be AAA, BBB, BAAA, and so on and so forth, right?
Yes, right.
And then like y here is basically just the number of games, right? So then knowing x, for example, I know the outcome is AAA. Of course, I know what is the number of how many games have been played, right? If like it's AAA, x is AAA, of course y is just equal to 3, right? And if like we have the x is, if for example x is a BBAAA, then y is just equal to 5, right?
Yes, right. That's right.
Yes. So because y is deterministic given x, then basically hy given x, what is hy given x mean is just like given x, what's the uncertainty of y, right? Given x, there's no uncertainty of y, right? So therefore hy given x is simply equal to 0. Of course, you can go through the compute like the probability and put it here and there, and then like write the entire thing. But
can we calculate first y and x, and then minus?
Yeah, of course you can. Yeah, but it's kind of redundant. Like if you think of this way, this is much easier, right? Because hy given x is this one. Then you can immediately write hxy, right? Because hxy is just x plus hy given x, right?
That's right.
And this is just 0. Then therefore it's just equal to hx. We already computed that, right? And this is just like 4.125. So this is a E part actually. I asked here in the E part. Then there's a C part here asking like hx given y. So now you have like hxy, then will be just hxy minus hy, right? So you have hxy and hy, then it's just equal to it's actually equal to 4.125 minus 1.56 is something like 2.57, something like that, or 2.56, something like that. As I said, of course you can start computing this first, I mean, drawing the entire probability, like do all the countings, but
If we counting that first,
you can, but isn't that much faster? What I'm saying, like, of course you can. You'll get the same result, but it's much faster, right?
I don't understand, but that D, I'm still.
Wait. Given y, given x, given any of these x,
Yes, that X.
y will be known, right? For example, like y, what is y defined here? Y is just the number of game plays, right?
Yes, that's right. 3,
So
4.
yeah,
5.
x is like whether you are having the outcome, whether you have AAA, BBB, and BAAA, and so on, right?
That's right.
If you have BAAA, then what is y?
That's, yeah, we have that's.
Let's say x is BAAA, what is y?
What's Y? 4.
Yes, right? So given xy is deterministic, right?
Given.
Given xy is certain, there's no uncertainty for y.
Yeah.
And conditional entropy, what was conditional entropy of y given x? It's basically just meaning that, just actually referring to like knowing x, what's the uncertainty of y, right? Knowing x, you know precisely what y is. Therefore, like this hy given x has to be equal to 0. Yes.
Yeah. Yes.
Yes.
So there is no. Yeah, there is no entropy in there.
Yes. Yes.
Maybe after this I have question.
Okay. Yes.
That's
Okay.
Take it
Yeah.
first.
Okay. So let's also look at the second problem. So the second problem is that basically you have D1 and D2 is the outcome of two dice, flowing two dice, dices, and then S is equal to sum of the outcome is equal to D1 plus D2, and then the question, it goes, the first one is what's the probability of, not probability, I'm sorry, what's the entropy of D1 given S equal to 3. So now this is again just simple counting here. So D1, D2 like two dices, like, so we assume like the outcome for D1 and D2 will be independent, and S is just the sum, right? So for S equal to 3, what can happen? Like I can have D1 and D2, I can have like value 1, 1, that will add up S is equal to 2, right? If I have like D1 is like 1, D2 is 2, then I have S add up to 3, and 2, 1 also add up to 3. Actually, only these two cases will get S equal to 3, right? So therefore, given S equal to 3, actually this only have like two possible events to get S equal to 3. So, and I'm actually HD1 given S equal to 3 is equal to probability, maybe I'll write it this way, probability D1 equal to 1, S equal to 3. Oh, this I cannot, let me move to a new page. So it'll be something like this, right? Minus log P D1 equal to 1, S equal to 3. I don't even need the summation here. My minus probability d1 equal to 2 s equal to 3 log probability d2 equal to 1 s equal to 3. Right? Only have two cases here, right? That's it, right? That's what. But here, like I guess some of you guys made a mistake. Oh, wait a sec. I'm sorry. Right, something like this.
Yeah, that is the summation of that.
Yeah, that's only two cases, right?
Cases.
Yeah, two cases. And some of you guys made mistake is saying that, okay, this is equal to 1 over 36 or something like that. Or like 1 over 6. It depends on how you're counting. But it's not right, right? Because I given s equal to 3 as a condition. Probability of d1 equal to 1 is not equal to 1 over 6, but it's equal to 1/2. Right? Because knowing that s equal to 3, d1 can only take two different cases, right? Either d1 is equal to 1 or d1 equal to 2. Right? So therefore, like this probability, d1 is actually 1/2 here, and this also equal to 1/2 here. So therefore, this actually is just one bit. It's like one. This is just one bit here. Yeah. So and then for part, I guess maybe I go to part C first. Like part C is easier. Part C is like h d1 of given d2 is equal to basically like d1 and d2 independent, right? So this is just equal to h d1. So right, because d1 does not depend on d2. So the conditional probability of d1 given d2 is actually just equal to d1. Do you agree with that? Yeah. So
yeah, but we can calculate not just like that.
Yes, but yes, but the point is like that will take you much longer time, right? More time, right?
Yeah.
It's once you look at that, you save much more. But you agree with that, right? This is like, or you can of course think of this. This is equal to h d1 minus the mutual information between like d1 and d2. And of course, like d1 and d2 independent, this is equal to 0. So again, this is just equal to d1. So then d1 is like just equally likely, assuming the dice is unbiased. So therefore, it's just equal to log 6.
Yeah. 1/6.
Yeah, it's like basically 1 over 6 log 1 over 6 minus, and then you have 6 terms of that way, times 6, and then you just get log 6. Yeah. And then for part B is basically part B, we want to compute HD1 given S, and again, we need to do some counting here, just more counting, similar to this one, but we just have to continue to count all the different cases. So we can have like D1, D2, and S here. We can have 1, 1 that get like S is equal to 2. If I have 1, 2, and 2, 1, that will get S equal to 3. And then I can have 2, 2, 3, 1, 1, 3, get S equal to 4, and so on and so forth, basically. You can see the pattern basically is for S equal to 2, you have only one case. S equal to 3, have like 2 cases. S equal to 4, we have 3 cases. S equal to 5, here you have actually 4 of them. Yes. And then you have S equal to 6, here you have 5 of them. and then s equal to 7, you have like 6 of them. S equal to 8, you go back to 5 of them. And s equal to 9, you have 4 of them, and so on and so forth. So therefore, like hd1 given s is equal to, this one I think is easier, just like compute it directly. So s is equal to 2 to 12, actually eventually go to 12. That's the only possible case is like 6 and 6, you only have one case here. So it's hd1 given s equal to small s here, let's say, and times probability s equal to small s here, and will be when s equal to 2, let's say s equal to 2 only have one case, so actually it's the entropy for that. If only you have one case, then it would be completely certain, right? So therefore, I mean d1 can only be 1, basically saying that. So therefore, like the entropy will be just 0 times probability of that is just 1 over 36. Actually, each of the event is like just 36, right? The probability. And then the second one is just log 2 times 1 over and 2 of them, right? 2 of 36, and then the other one is like this, have like log 3 times 3 of 36 and times 4.
Why there is 0 in there?
Huh?
0. That's D1, D2, D1, S. Oh yeah, that is S0, S1. This is a s equal to 2, yes. S equal to 2, then hd1 given s equal to 2 is just 0, right? Because d1 can only be 1. Yeah.
That's completely certain. And for this s equal to 3, then you have two cases, therefore like the entropy is log 2. S equal to 4, that's 3 cases is log 3. S equal to 5 would be like log 4. Log 4 times 4, 36. That's log 5 times 36 plus this is a log 6 over 36, and then you're back to like log 5. That's for this case here, I think like 5 over 36. That's log 4 over 36. That's log 3 over 36 plus log 2 over 36. That's log 1, that's 0, 1 over 36. Then if you compute that, the whole thing should be like 1.89 something, or like 1.8955 bits. That's for the first two problems. And for the last one, I don't think like any of you guys has real problem. Just like some of you compute that, like probably you put into the computer, you just made a mistake like doing the computation. The website is very simple, right? You just pull out the equation there. So if you're a sigma, the first question, I think the sigma is, I forgot, how does that, like, maybe it says something like that, I forgot. That's the coherence matrix for a random variable, joint Gaussian random variable x that contain like two kind of random variable x and y. Then we ask what is hx and matrix y and so on, and then hy given x, I say, and then hx will be just because sigma is like that, then sigma x squared is just this term is just equal to 1, right? So therefore, like h small hx is just 1/2 log 2 pi e sigma square. That is just 1/2 log 2 pi e is just 2 points. It's approximately 2 bits basically. And then like for hxy will be equal to 1/2 log determinant 2 pi e sigma. Yeah. If you put into the computer, you get like 4.5 something bits. And then like for C part, this is A, B, C. C is a hy given x is just xy minus hx. And this will be like 2.487 bits. Okay. Yeah, that's the homework. Guess you guys probably have no questions. So let me go back to what we discussed earlier. Oh, actually, we were talking about typical sequences, right? So, one final remark about the typical, not final actually, just one remark I'd like to talk about the typical sequences. Think of what we talked about for the source coding theorem, that we have a discrete memory-less source. We argue that like, if we have an encoder there, and try to compress this source, we say that like, we can compress this source into hx bits, right? This thing, how can I? Oh yeah, okay. So my handwriting is so bad. I can compress this into hx bits. Right. Now, okay, using a typical sequence argument, we remember like how we did that like earlier. Basically, we say we have this. We introduce the Crafts inequality, saying that like okay, we need the Craft inequality. For the code, we need to satisfy the Crafts inequality, and only when we satisfy the Crafts inequality that the code will be uniquely decodable, and then we try to minimize the expected length of the compressed code given the constraint of Craft inequality, and we go through and we went through the Lagrange multiplier, like basically using the KKT conditions, and we eventually solve that, and we find that the optimum, the minimum length will be just equal to the entropy hx here. But this has a much cleaner, but it's not, I would say, like slightly less rigorous argument, just using the typical sequences here. So we just say before the break, we have the typical sequences here. So like discrete memory-less source here, we're saying that we pull any sequence from this source here will be typical. And each of them, and basically how many typical sequences we have is like 2 to n hx, so many of them, right? So say if I have pull like n of them, then there will be like 2 to n hx so many sequences here. So then the compression will be really easy, right? We have like 2 to n hx so many of them. We just like assign a label for each of them, right? Then how many bits needed to store this label will be like, assume that we are not going to I mean we don't use any entropy coding. What I mean is we are not using any further compression. then just trying to come to store like 2 to the n matrix labels, we just need like log 2 to the n matrix bits, right? But 2 to n matrix bits is just equal to n matrix bits, right? So that means that like for a sequence of length n, we just need n matrix bits to store the sequence. So therefore, like per symbol, we'll just need matrix bits, right? So this is a super fast argument with the typical sequence argument that we discussed. We introduced before the break. And now let's continue to discuss the typical sequence, but now instead of like just have one sequence coming from one source here, so we are going to talk about something called like a jointly typical sequence or joint typical sequence. So we have like a joint source here, let's say pxy here, and I pull out like 2 sequences at the same time. Now we want to try to characterize like these joint sequences. Basically, you can think of like x and y as like a pair of symbols that you can consider a pair at the same time, right? So actually, we can elaborate our argument, use our argument like immediately to conclude that like I can have define something like a joint typical sequence, something like that, like consider like pair of sequences xn and yn. The probability to be less than like 2 to minus n hxy minus epsilon and bigger than equal to 2 to minus n hxy plus epsilon. We say like any sequences satisfy this condition to be jointly typical. So basically like we'll also like actually we are also like to complete our argument, like we also need xn and yn to be typical themselves. So therefore we also like need to the earlier condition that basically like hx epsilon to minus n hx plus epsilon and also like pyn. So basically, like if these 3 conditions are satisfied, we say like xn and yn are joint typical. Xn and yn, joint atypical. And of course, this is again some kind of a tautology or oxymoron that this we introduced that, but any joint sequences pulling out of that source is essentially a jointly typical. So basically, any sequences joined from this source are jointly typical, but often there's something that we have some particular interest to look at. Is we have a joint source pxy here. We know that like we pulling any sequences from that is jointly typical. how about like the sequences like are actually at the beginning are not really pulling from this source here, but instead we have like a fake something trying to fake this with like two independent sources like px and py, and we want to know like what's the probability like for sequences joining from this will be jointly typical under this definition here, under this definition here. So yes, what's the probability that this is jointly typical? So okay, I guess this seems at this moment a little bit weird why we want to look at this, but
that the box is always has joint typical.
yes, I mean, yeah, if you have source coming from this will be always jointly typical, but if you are not actually coming from this, but you are coming from this instead, then of course it doesn't necessary to be jointly typical, but there's also chance to be jointly typical, right? Because jointly typical is just any joint sequences satisfy this condition, right? There can be some sequences join from this one but satisfy this condition here.
Yes.
So this is kind of useful, like as you will see later on, is especially in terms of channel coding. That is like you're trying to transmit signal through a channel, and we can use some of this argument to describe why the capacity of a channel is given by whatever that expression. So but let's look at what's the probability that we have sequences are actually typical but independent themselves, but turns out to be jointly typical. So probability that x n and y n to be okay, to be jointly typical okay, I don't know what's going on. So it's equal to did I hit something? So basically I can sum over all the I'll probably be careful, this is a big X here, but this probably should be small x here. So do you agree with that? This is just what's the probability would be simply sum of each of the probability of each of the possible outcome, right? The probability this in this set will be just sum for whatever sequences that are jointly typical, and we sum up the probability for all of them, right? That would be that probability, right? So but then because we assume these are independent, then we can weigh it as pxn and pyn, right? Now, and then this will be less than equal to this again, it is just sum here yn xn yn in a epsilon n.
That is always given by that.
This is a given, right?
Yes. Doesn't mean that this
Oh,
this expression is given by this one. That's mean that that these guys and then have correlation with joint typical.
Not necessary because this is just okay. It's again this is a set notation, right? It's just like this kind of like a set x satisfy some fx, something like that, right?
Yes, yes.
Satisfy fx equal to a, something like, for example, this is just set notation, right?
Yes.
It's like for all the sequences in the jointly typical, so it's like just. Or of course I can just write like some yeah, actually it's like kind of redundant, I can, but it's like clearer to write it this way, I guess. So it's basically just summing over all the sequences that are jointly typical. Just think of like what's the probability of let me give an example. Probability you throw a dice, outcome is odd. Let's say I throw a dice, and what's the probability outcome is odd? That would be like sum over probability that basically sum over x, outcome is odd, right?
Yes.
Px, something like that, right?
Yeah.
That would be like something like p dice is 1 plus p3 or p5, right?
Yes.
And this is exactly just doing this. There's nothing really fancy about that. But then this probability, because x in reality xn and y are independent, right?
Yeah.
So therefore I can split that, and since I can split that, I'm also like xm and yn are typical, so therefore like it will be less than equal to 2 minus n hx minus epsilon, and 2 to minus n hy minus epsilon, right? And then so I can pull this out. It will be like 2 to minus n hx plus hy minus 2 epsilon. But then I have like sum over 1 this here. But this again, this will be just equal to the size of the set of typical sequences, right?
Yeah.
Joint typical sequences. But what was the size of joint typical sequences? That would be less than that would be less than, okay, this would be less than 2 to the n h x y plus epsilon, right? Agree with that?
Less than, yeah.
Yes, that will be less than this way. So therefore, I will have the total thing will be less than equal to 2 to the minus n hx plus hy. So this is plus 0, so I have minus hxy. This is a epsilon. This is minus epsilon, so we say minus 3 epsilon, something like that, right?
Oh yeah.
Yeah. So but this is just ixy, right? This is just ixy. Hx plus hy minus hxy is just ixy. So yes.
Where is come from 3?
You mean this 3?
Yeah.
This 3 because there's 2 here, there's 1 more here.
Oh.
Yeah. So just add up to 3.
Yeah.
So I will have like, so therefore this is a less than equal to 2 minus n ixy minus of the epsilon. Actually, we can repeat a very similar argument. So basically, let's see, we maybe try to. Oops. Oh, you. So we can repeat the same argument, but we just try to change this to the other side, right? Let's see. We can say probability of, let's see, okay, I have more terms earlier probably. Let's say this. This is a little bit hard to move around. Okay, I can do it this way. So we have this is equal to this, just we discussed earlier, but sum over this one, again we can split this, right? Split this into this one is bigger than equal to 2 to the n, then I can this minus I change it to plus, right? Yeah. Pxn, Pyn is bigger than 2 to the minus nhx plus epsilon, yes.
Yeah, that's right.
Then I have sum here, then I have plus here, and then again I have this is equal to the size of the joint typical sequences. But of course the size of this one can say is bigger than equal to minus epsilon. And remember I have a 1 minus delta here, for the other side. It's bigger than 1 minus delta, something like that. So then therefore if I this I don't need that. I combine everything will be bigger than, so it's eventually will be bigger than 1 minus delta 2 to the minus n hx ixy plus 3 epsilon. Yeah. So basically just you have 2 epsilon here, 1 minus epsilon here. Again, you put down there will be 3 epsilon here. But honestly, these are not important. The important part is is this one, the exponent here. Basically, if you look at you initially have 2 independent typical sequences, and you want to see what is the probability that they are jointly typical, the probability will be approximately 2 to minus n ixy. And of course, if it depends what is the original distribution at pxy here. If the original distribution are independent, then of course any independent typical sequences will be jointly typical. Then in this case, this will be ixy will be approximate, will be 0.
Yeah.
Then we're just saying, okay, this will be bounded by 1, something like that. Then of course it is obvious. But if pxy initially are correlated, then ixy will be bigger than 0, right? So then if it's more correlated, then the probability that this initially independent sequences to be jointly typical will be have a lower probability.
So if there is correlated, it means that I will be bigger than 0.
Yes, and more correlation, or if they are more dependent, then the mutual information will be larger, right? So that's basically ixy is more or less measure the amount of independence of x and y, right? Kind of.
Or when the independence will be larger, then not there is a correlation there.
Dependence will be larger.
Yeah, will be larger.
Yeah, it's a kind of fun. Okay. This is like we say stuff are correlated. That means it's not independent, kind of like.
Yeah.
Yeah. So it's a kind of, I guess. We didn't define here very kind of precisely, but basically like x and y are correlated, then they are not independent, right?
Yeah.
Correlated, or I should say that x are not independent of y, then we say x and y are correlated, right?
Yes.
Yeah, and but when we say uncorrelated, it's more have a more kind of rigorous definition. Or like actually, I shouldn't say that. Like I mean, I think here also have a rigorous definition for that, right? Remember, like when we say x and y are uncorrelated, like we need that. That's the condition to be uncorrelated, right?
Yes.
So if it's correlated, that would be like not zero, basically, non-zero.
So it means with this, if correlated, it's when that we can compress it more because the entropy.
Yes, they together. If they are okay, depends how you say. Okay, yes, it's true. Yes, if they are it depends on the setup, right? If I'm going to compress x and y together at the same time, if they are they're correlated, then like it'll be assuming that like hx plus hy is fixed.
Yeah.
Assuming that, then hxy will be less than hx plus hy, right?
That's right.
Yeah, because hxy is equal to hx plus hy minus ixy. So if x and y are not independent of each other, then this one will be bigger than 0. Then hxy is less than hx plus hy. Then we can, yeah, potentially we can compress it more, because if we are going to compress them together, the theoretical bound will be hxy. Yeah.
So how to know that's correlated? There is mutual information or not between x and y.
You can, okay, if you have the joint probability, you can just compare it, right?
Yes, right.
Yeah, if you have like pxy, you have the joint distribution, you can just compare it, right, with like what you did in homework and so on.
Okay.
Yes, and also like if you only have like some, if you don't have, of course that's the whole point, like the distribution itself has lots of information, right? Because this is like for every x and y you have this is basically a function, right?
Yes.
But if you only have the mean and variance, or like then you can verify probably with just whether your variables are correlated or not,
Okay.
right? But even the variable is not correlated, like this one is satisfied, it is still doesn't guarantee that like x and y are independent. But yeah. But if of course if x and y are correlated already, like this is not 0, then you can definitely say okay, x and y are not independent. So now it's getting a little bit. Let me talk about two lemmas coming from what we discussed from here. That we talk about like two independent sequences and what's the probability that they will be jointly typical. So first, let's talk about I probably only can finish one of them, or like maybe it depends on how. Let's discuss something along at the packing lemma. So what the packing lemma does is saying that, okay, if we have a discrete memory source again, and now we're going to draw sequences from this source. Instead of just drawing one sequence, let's say I draw like m sequences. So I draw m of them from here. And the question is like, what is probability that none of the drones Johnny typical with one another. So it's like we draw m sequences here from here, and then we want to see how many. Basically, what's the probability that like none of these sequences like that we join will be Johnny typical with each other. So in the sense it's called packing, because you think of like drawing that and then you put them together, and you want to see like how many of them you can pack while these kind of sequences putting together are still not Johnny typical with one another.
That's following the rules above, that the entropy is 2 minus nh.
Yes, it's kind of similar to that actually. So, but let's go through that like more kind of clearly. So let's say like let's consider like if we think of this, let's consider this question. Or like actually this question is more or less like how many we can pack, right? Can pack independent sequences.
Independent sequences.
Yeah, I think that.
Yn in that?
Huh?
Yn?
Yn? Yn? Oh yes, Yn. Each of them are Yn.
Yeah.
So here we set m, but like, but the question is more or less like that, like how many we can pack independent sequences such that they are not Johnny typical. So we know that like if we just pick two sequences, like it would be like 2 to the minus n I something like x xy, stuff like that.
That is Johnny typical.
Wait. Maybe maybe I was wrong about the setup. Sorry. I was wrong with the setup. So I should say like I start with an xn. I think of like maybe a box or something, like you have already one sequence is xn here, and then you pack this yn into that. Same things together, consider them together. Sequences. Packing.
Okay.
Pack them together. That's why people call it packing lemma, right? So you put this yn together, like consider with this xn. I should say how many yn we can pull such that they are not Johnny typical with xn. So we basically have a xn here, xn is something here, and then we from a discrete memory source we draw this source have like distribution py here. We draw sequences from there, get some yn, and we want to see like how many we can draw. Of course, we know that like if we just pick one of them, the probability is just 2 to the nixy, right? So therefore, like if ixy is bigger than equal to 0, I mean in the sense like or like bigger than 0, if x and y, ixy is x and y are independent, then as n goes to infinity, of course, that probability is very small, right? But if we pack many of them, then ultimately this probability will be non-zero. Will be
Bigger.
we can't find a bigger, right? So then
we pull and on that from there.
yeah,
We
pull n sequence there,
and
m length n sequences there, and
so actually there is xn with m, then we can pull m sequence xn there.
yeah, let's say we put m, but but more like a how many sequences we can pull, can't think of, like, but let's fix this to m first. Then let's see like what's the probability that if we fix m of them, like any one of the m sequences, myn are jointly typical with xn. Yeah, that probability would be just m times the probability of xn, yn jointly typical, right? And that is just from the discussion earlier, it's just less than equal to 2 to nixy minus 3 epsilon. So we can kind of like define m as 2 to the nr. So in the sense that as n increases, less of n increases, of course we can pack more sequences there. So m, we expect m will be like kind of exponentially increases with n as well. So let's try that. Let's pick m equal to 2 to nr. Then if we set that, then this will be equal to 2 to the minus n ixy minus r minus 3 epsilon. So then, as you can see, like what we have is like this will be goes to 0.
What is r there?
Okay, I just redefine m as like 2 to nr, or like r is just equal to log m over n. Yeah, basically r is equal to log m over n. So if we say like r is equal to log m over n, and then we substitute back into this one. So what you see is like as long as r is less than ixy, so I assume that epsilon is pretty small. So or like or you can even say, or you can write this. So then basically like this will goes to 0, right? Because then this will be negative. Sorry, this will be positive. N goes to infinity. Then this will goes to 0, right?
Yes, yeah, that's right.
So therefore it means that like as long as we choose r to less than this, then we can make sure that like none of this y that would pull out from that will be jointly typical with xn here. So this is like kind of a packing lemma. So and I guess I next time I come back we'll talk about
So it
very
means
similar
that
lemma. Yeah.
n should be bigger.
Yeah, m should
M.
grow. M should grow. You mean m or n?
And
N?
yeah, n should be bigger to get r less. So this
Oh
one-
no. Okay, so that's the other way around. Actually, r will be fixed. R is fixed. How we are going to use this actually? R is fixed, but n goes to infinity. Yeah.
okay.
So therefore, m will goes to infinity as well. Actually, kind of. So, but r is like kind of like why we use the symbol r is we think of weight. So
So how to calculate r then?
actually we don't need to calculate it's basically we have a constraint for r. It's like r should be less than the mutual information. So as long as it's less than the mutual information, then yeah, you can pack as many of like less than the mutual information basically. Yes. So I guess I will stop here again. We'll have homework probably like today or tomorrow. I'll put it up and then like yeah, and then like it will be due like what next weekend or something. Yes. So I'll see you guys. Actually, I'll have like also through this Zoom. I guess like next time also. So I'll stop now. If yeah, okay. I think it's here.